So here's the answer to number 3. I'm going back in my videotape. Here's the answer to number 1. And please do number 2 for homework. So please do number 2 for homework, worksheet 3. Here's the answer to number 1 for 3A. Now we're working on 3B. Let me know when you get 3B done. I mean, did you get the first one done? The first and force normal?
Yeah.
Because you're going to have 2, because remember, it has basically 2 circles. There's a circle at the top and a circle at the bottom.
I got the 5 one. The 5 meter one.
Okay, now my numbers are going to be a little different than you because I used 1,000. So you're going to have to take this number right here. So if they don't give you a mass, you have to pick a mass, and the mass I picked was 1,000. So if you picked 100, you're going to take this. You're going to get 16.2, right?
I haven't done that one yet. I did the 22 and 5 one.
Oh, okay. If you did the 22 and 5 one, I chose 1,000. If you chose 100, you're going to get 16.2 as well. So here is the other one. You're going to get 106.6 if you chose 100. I chose 1,000. But the thing that we're going to do is compare them. What do you notice between these? If you take this number divided by that number, what do you get? So you didn't get this? Well, that's because I used 1,000.
No, I know, but I didn't even get those numbers. Like,
Do you have a mass here?
but I did the same. Like, I got the same.
Do you have this right?
Yeah.
You have 9.8.
Yeah, I got all that right. Still.
And this. And then you make sure you put minuses in front of both things.
Oh, that might be it, because I was subtracting it from.
Yeah. You'll end up.
So it would be negative.
So it would be
Plus.
negative 9.8 or 9,800 plus this.
Oh.
Now, if you compare these two numbers, it doesn't matter what you get. Whether you get, if you use 100 or 1,000 for your mass, you're still going to notice that that one is nearly 6.5 times larger than the other one. Do you notice that? So one is 6 times larger, nearly 7 times larger than the other one. So why would you want that loop? Why would you want a clockoid loop? Here's your numbers. What is your reason?
You can turn with 6 or 7 less amount of distance, so you might turn sharper.
Okay, so are you trying to say that you can have a faster velocity here, because then you got to go through you have to have enough velocity to go through your turn, right? But then why don't you want to have that velocity down here? Why wouldn't you want to have a larger velocity down here, or a small velocity down at the bottom?
So you pick, like, you want to gain speed so you can get through the rest of the run.
Right, but why wouldn't you want a fast velocity down here? What's that fast velocity going to lead to?
Even faster velocity.
No. A fast velocity leads to a
More friction?
more friction, a stronger force, doesn't it? Doesn't it?
Yes.
Because there's more acceleration. And what is that force on?
Tracks. The people.
You. Are you going to be able to tolerate a force that's 6 times greater than the force you were feeling up here? No. So that is the reason why, and that's the answer to C, the reason why these roller coasters have this shape is because you need enough velocity to get through the curve up here, but you don't want to have that much velocity down here because that's too much force and your body's not going to be able to tolerate it. You're going to end up with internal bleeding. And that's not any fun. All right. Number 8, Tarzan. Look at the predicament poor Tarzan is in. Has anybody watched the new Tarzan movie? You haven't? It's good. It's a kid's movie, I think, but it's a little violent for a kid. So Tarzan gets himself into a predicament, and he runs into a branch. And notice how his circle changes. It goes from 8 to 2. So it says, as Tarzan swings from point A to point B, describe qualitatively how the tension in the vine changes and why.
I think there's less tension on 8 meters, and there's going to be more on 2.
Okay. And what is your reasoning for that?
Because the rope is longer than the 8-meter one, so like it could distribute more, I guess. But then when it hits the 2-meter, all the other 6 meters that is gone now, and now it's just hanging out with 2-meter.
Okay, that was a very good description. Can you go back to your centripetal force equation? What are you grappling with? Are you grappling with mass, velocity, or radius? Radius. So your description is connected to the radius. And what is radius? Radius is what type of proportion to force? If the radius goes up, what happens to the force? Does the force go up or down? Down. So it's inversely proportional. So you are correct. Then that force is inversely proportional to the radius. And that's how you would answer that question. The speed does not change. The radius does. And if you change the radius from 8 to 2, it's going to be 4 times greater for the 2 than it would be for the 8. That's hard to believe, isn't it? Okay, and then we go to B. It says at B, he's swinging at 7 meters per second, and the vine is 8 meters long. How hard does he have to hang on the vine to keep from slipping off? Okay, so you need to do a force diagram, and you need to find force T. So for here, how do you find force T? Go ahead and set up your net force equation. Draw a net force. If he is, right here at B, what would your net force equation be right before he touches the branch? So the branch has nothing to do with it at this point. So what would your force diagram there be? Can you tell me? Not quite. He's at the bottom of the circle. That would be at the
So
top.
it's going up.
Up, the force tension's up, and what's down?
Gravity.
Gravity. So draw your force diagram. Force tension is larger than gravity at this point because you're at the bottom of the circle. Then set up your net force equation and fill in your numbers.
So instead of force normal, it's force tension.
Yes.
force negative.
then that force is going to be positive. Because the tension is larger than the gravity.
Okay, if they're equal, is it still positive?
It's 0.
It's okay.
So your answer should be like this. I did it 2 different ways. So here's your force diagram. Are you good with this? I filled in my numbers. If you use 10, you're going to get this. If you use 9.8, you're going to get that. Do you agree?
Yep.
Are you starting to feel better about these problems?
Yep.
Now, do part C the same way, but now the radius of your circle is what? 2. So do the same thing for part C, except now your radius is 2. Okay, so here's C. Shouldn't have taken you that long. Same deal, except I'm going to change my radius to 2. If you use 10, you're going to get 2,800. If you use 9.8, you're going to get 2,744. Notice the difference in the forces. Do you notice that? A lot of people have trouble with that. They think, oh, the larger the radius, the larger the force. Not true. The smaller the radius, the greater the force. Okay, good question. If Tarzan slips at point C and the rope breaks, what is his motion going to look like here? This is a learning thing. This is a conceptual. So we got inertia. He's going to go straight out, and then what's he going to do?
Start to fall.
Then he's going to do a parabola. So he's going to go straight out and go down. So you want to draw that in there. Okay? He's not going to go straight down this way, and he's not going to go back like that.
It makes sense though, because like when you jump off the swing, you go like that, and then you start to fall.
Very good. And the swing is a circle.
Uh-huh.
Okay, so put a star by number 5. Number 5 is homework. Okay? And then we're going to do number 6 together, which is kind of nasty.
Oh gosh.
Nasty but fun.
Oh, I love this.
Have you ever ridden on this ride?
You like it like
yes.
you spins and you're
Yeah, at Adventureland.
Okay, so you're going to have to draw from your experience at Adventureland. The floor completely falls out.
Yeah.
So why aren't you falling?
It's the same thing as
Inertia.
the mug.
It
with
is
the
inertia.
Water.
What?
It's the same as the mug with the water.
With the bucket in the water, yes. So it's the same thing with our celestial bodies rotating around Earth. The reason why Earth doesn't go into the sun. Okay? So we have to mathematically prove this. And notice this little devil right here is involved, friction. So this is going to be a technical. It says an amusement park ride operates as follows. The rider enters the circular structure and is stationary with the floor at point marked A. Then they stand against the wall as the cylinder begins to rotate. When it's up to speed, the floor is lowered to the position marked B, leaving the rider suspended against the wall high above the floor. So the floor drops out. So here's the mass of the rider, here's the radius of our circle, and here's friction. So what would our force diagram for this be? So let's draw this. This is different because normally we're used to tension and all that good stuff. So my rider is my point mass. So we have the weight of the rider. Do you agree? The rider has something pushing against its back. So that's going to be our force normal. Right? Do you agree? So this is the back that you're resting your back on. And then what is making the upward force? It's not a force normal because there's no floor there. Friction. So it totally depends on friction. So if you put a whole bunch of goo on your back and you went on this ride, it won't work.
Just fall.
Which worries me because some people are really sweaty.
So if you're sweaty, you're just gonna fall.
But they make you wear a belt. Like, they make you, like, wear, like...
Oh, they make you wear a belt
I
now?
hope so.
Oh.
So like, it's like you lean against a thing and there's, like, bars you can hold on to. And then there's, like, something... Like,
Oh,
it's like
when
a
I was
seatbelt
a
kind
kid, there was no belt.
So you just.
There was no
So if
bar.
you're
But the
sweaty-
floor doesn't go down that far. Like, if
it
it
only
goes
goes
down...
2 feet.
Yeah, if even. So, like, you really wouldn't get hurt if you...
Because I remember specifically seeing grass.
Yeah. This one is a bit dramatic, how far the floor falls.
It is very
Because
dramatic.
it's like... this.
Okay, so here's our force diagram. So this force right here is the one that everybody has trouble with. That frictional force between your skin or clothes and the back of what you're leaning against, that's holding you up. And actually, these are equal.
So, force
So
normal
the force normal is the winner.
That's our centrifugal.
But it's interesting because we still have mu. And where does mu fit into all of this?
Friction.
Friction. So let's go ahead and calculate this. We're going to have to do it on 2 different levels. We're going to have to do it a y one, and we're going to have to do an x one. So our forces in the y direction are friction and gravity, and our forces in the the x direction is just force normal. So which one is involved in our circular motion? The actual circle.
Oh, X for...
This right here is the circle, so that's where you're going to be putting in the m
Okay.
v squared over r. And then this right here is just going to be our normal ma. But we notice that these are equal, so what is this going to end up being?
0.
0. So now my friction is going to end up being equal to my mass. My weight, I mean. So I ran out of room here. So now I can start filling stuff in. I know that friction is force normal, times mu. And I know that my weight is mg. Are you with me on that? So that was a big jump. Do you see what we did there? We're like, oh, we have no idea how we're going to figure out that force normal.
You just cancel stuff.
And I'm going to end up finding it out here, and then I'm going to put it in there, and then I'm going to be able to find my velocity. Do you see how that works?
Yep.
So I'm going to solve for this, because I have everything else. So Fn mu is 0.5. My mass is 73. So plug and chug for me, and tell me what my force normal ends up being.
I got 1,430.8.
1,430.8. Do we agree on that?
I agree.
Okay. now, now I'm gonna take and bring this into here, right?
Yep.
And I'm gonna find the velocity.
What's the R? 1.5.
Make sure you take the square root of that.
Would you first multiply by 1.5 to get rid of this?
Yes,
Okay.
definitely. So you're gonna multiply by 1.5 on both sides, then you're gonna divide by 73, and then you're gonna take the square root of it. And I got this.
Thanks.
So it's not as bad as we thought, but it's a nice little twist. So friction makes a difference. So you're going to have two things to do for, well, three things. Yeah.
So whenever you get like a force diagram like this, where there's a y and x component, you have to break it down.
I would.
Okay.
Especially if you know for sure there's no way for us to find FM. I know I'm going to end up doing a substitution.
Okay.
Which is why I taught you this. I specifically taught you this because of that.
Okay.
Because if you write both of these equations, big things open up. If you don't write these equations, then you're kind of lost and you're out wandering in the woods. Okay, so three things. You got to do number 3, number 5. Okay, and you have the rest of the time to do that. And then the next time you come to class, which is Friday, you're going to have a quiz. Okay? So 3, 5, and study for a quiz.
Do we have this class Friday?
You do.
Okay.
Did you get that, Connor? Connor.
Yeah.
Okay, you're welcome. Do you have any questions? You can do 3 and 5. And study for your quiz, okay?
Do we plug?
You're going to pick a number.
Yeah, I did all that, but I don't really.
You're going to put it into v squared over r.
Oh, so not the AC equals v squared over.
Well, you're going to use, are you doing the acceleration one or the force one?
Acceleration.
So you're just going to put it into v squared over r, and that's a. Remember?
Yeah, so is v squared, is that the m they give us or the r?
The v squared, so you have to pick a v.
Oh, so I just can pick whatever.
Pick whatever number you like. Well, actually, you're going to end up calculating.
I just don't know where to start because I did the m equals 100, r equals 10, so I still know that. Now I don't really know.
Okay, so you have r.
Because, like, I don't know what path we're at.
How do I explain this? How do I explain this? I'm gonna look and see what I wrote down. V is all the same.
So I just pick a v.
Pick a V and then the number doesn't change.
Okay.
Does that make sense to
And
you?
then I'm dividing it by.
And then you're going to put it into that equation that you have there.
V
And
squared
you're going to
over
divide
R,
that by the R's that you have.
So like
It's
the
v squared
5
over
or
r,
5 or 6
It's
or
V squared over R. So pick a different V. So I would pick 10. Okay, so V is 10. And you're just going to do all those problems with V being 10. And then you're going to change the R.
Okay.
Okay? Does that make sense to you, Bailey? So what this is you're going to say, which one do you want to do first?
Would it be mv squared over
So
r?
you're going to do A.
Okay.
So you have 4 times R. What is your R? And then So you have, what do you want PT? So 10 squared, 40.
Would it be MV squared
And
though?
then that's gonna be that, that would be the A for this point.
Okay, and then for this one, is that negative 40?
No, you would just do 40 again, because you're gonna notice that these have the same acceleration, even though they have different masses. And that's what we want to do.
Okay. Gotcha.
Would it be MV squared?
V squared times R
Yeah.
for the force, yes. But not the acceleration.
Okay, well
The
then,
acceleration is V
are some of them
squared
gonna be
over
the
R.
same?
They are, and that's why it says there will be ties. Do you see that?